Hey everyone, and welcome. Today, we're going to pull back the curtain on the secret language of our digital world, data structures and algorithms. And look, this isn't just for programmers. This is the hidden logic that makes pretty much all of our technology work. Let's dive in. So let me ask you a question. It kind of sounds like the start of a joke, right? What could your GPS finding the fastest route, your social media feed, and that simple little undo button possibly have in common? Well, the answer is that they all rely on really, really clever ways of organizing information. So what even is a data structure? The simplest way to think about it is like a blueprint or maybe a super specialized filing cabinet for information. See, it's not just about storing the data. It's about arranging it in a way that lets us use it super efficiently. And that arrangement, that's the key to everything. And we need them for all sorts of things. On a basic level, they store everyday info, like the contacts list in your phone. But they're also these incredibly powerful tools for programmers, and they can even model insanely complex things, like a map of all the roads in a city. Okay, so let's start with the absolute fundamentals. Pretty much everything else we're going to talk about is built on the ideas behind two basic structures: arrays and linked lists. You can think of them as kind of like the foundational building blocks of the programming world. First up, we've got the array. And honestly, it's pretty much exactly what it looks like here. A single, long row of boxes, all stored right next to each other in memory. Each box gets a number, it's indexed, so if you want to know what's in box number 4, you can just jump straight to it. Instantly. This makes finding things incredibly fast. Now, for a totally different way of thinking about things, meet the linked list. In this case, each piece of data, each node, can be stored literally anywhere in the computer's memory. The magic part is that each node also holds a little pointer that tells you exactly where to find the next one in the chain. It's kind of like a treasure hunt, where each clue leads you right to the next. And this brings us to one of the most important ideas in all of computer science: trade-offs. There's almost never one best way to do something. An array, for example, is lightning fast for finding things if you know their position. But if you try to add or remove something from the middle, it's a huge pain. You have to shift everything over. A linked list is the exact opposite. It's slower to find an item because you have to follow the chain, but adding or removing one is super easy. You just change a couple of pointers. It's all about picking the right tool for the job. All right, now that we've got our basic tools, let's look at some specialized organizers. Stacks and queues are a lot like arrays or linked lists, but they come with very specific, very important rules about how you can get the data in and out. Before we even touch the technical terms, just look at these two images. They tell you everything you need to know. On the left, you've got a stack of plates. You always put a new plate on top, and you always take a plate from the top. On the right, a line of people. First person in line is the first person to be served. These two simple ideas are unbelievably powerful in the digital world. So let's make it official. That stack of plates represents a principle called last in, first out, or LIFO for short. The very last thing you put in is the very first thing you have to take out. Simple as that. And believe me, you use this concept all day long. Adding an item is called a push, and taking one off is a pop. Think about your web browser. Every time you go to a new site, that page is pushed onto a stack. When you hit the back button, the last page you visited gets popped off the top. The undo button in a text editor, yep, that's a stack too. Now, for our other organizer, the queue. This one works on a first in, first out principle, or FIFO. This is just like that line of people. The first one to get in line is the first one to be helped. It's all about being fair and keeping things in order. Adding an item to the back of this line is called NQ, and removing from the front is DQ. This is exactly how your printer handles jobs. The first document you tell it to print is the first one that comes out. It's also how customer service chat systems manage all the people waiting for help. Okay, so far we've mostly talked about the structures themselves. You could call them the nouns of our digital language. But what about the actions? How do we actually do things with this data, like searching or sorting it? That's where algorithms come in. And we're going to look at one of the most elegant and kind of mind-bending ideas in all of programming: recursion. Honestly, the best way to wrap your head around recursion is to look at these Russian nesting dolls. Recursion is just a technique for solving a problem by breaking it down into smaller, identical versions of the exact same problem. You solve the smallest one, which helps you solve the next one up, and that helps you solve the next one, and so on all the way back to the top. When you get down to it, the logic just has two parts. First, you have to know your base case. That's the smallest doll, the one that can't be opened anymore. It's the simplest version of the problem you can solve directly. And second, you have the recursive step. This just says, hey, If I'm not the smallest doll, I'll just apply the same exact logic to the next doll down. You just keep doing that until you finally hit the base case. All right, let's level up. It's time to talk about the structures that help us model our messy, complicated, interconnected world. When a simple list just won't cut it, we turn to trees and graphs to show how things are related. A tree is all about hierarchy. It starts at one single point at the top, the root, and everything else branches out from there. It looks just like a family tree or a company org chart. The most important rule here is that the branches always go down. They never, ever circle back and connect to something above them. The file system on your computer is a perfect example of a tree.
And the terminology is pretty intuitive, which is nice. The very top node is the root. The connections are called branches, and any node at the very bottom, with nothing branching off of it, is called a leaf node.
And last but not least, we have the most flexible, most powerful structure of all, the graph. If a tree is a strict top-down hierarchy, a graph is a free-for-all network. It's just a collection of points, or nodes, and the lines or edges that connect them. Any node can be connected to any other node. There are no rules. And this, right here, is where you really see the power of these ideas. Graphs are the invisible engine behind so much of our modern lives. Your social network? That's a graph, where you're a node and your friendships are the edges. When your GPS finds the best route, it's using a graph of roads and intersections. The entire World Wide Web is just one gigantic graph of web pages all linked together. So there you have it. From a simple row of boxes to these incredibly complex networks, these are the fundamental building blocks that let us solve problems with technology. They're the invisible architecture running behind the scenes of almost everything you do, which kind of makes you think, now that you know the tools, what problem would you want to solve?